And so, again, we came out here in 2009 trying a lot of different techniques, many of which didn't work, but some of them did work very well. And just to point out the glaciers that we're looking at, so you can put that down for a minute if you want. Arms don't get tired. But over here is the whole thing is called the Gornergletscher, or in German, Gletscher system. You might think it's easy to get out here like just walking down there. Distances are a bit deceiving. What we would usually do, just to give you a context for how we do our work, is that we'd get off at Rotenboden, just like you did, and then we'd walk about a couple hours along this trail, down, 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 so it seemed quite easy because it's going down, to where we would get to where the valley would meet the Gornergletscher. And then there's a series of very steep ladders that are bolted into the rock, and then some ropes that have been there for a while that you carefully sort of ease yourself down. And then you used a combination of skill and nerve. I had mostly nerve, not so much skill. And sometimes nerve can make up for skill to sort of jump or ease yourself onto the actual ice itself. Now, as I was last year a couple of years ago, it was quite tricky to do that. You had to be fairly agile, so that means there was meeting limits in my ability. But I understand that you can no longer do that. The ice is separated so far that you cannot just sort of ease yourself or jump or whatever onto it. If you have special equipment or more nerve and more skill, perhaps you can. I haven't been down there since 2 years ago. If you were to walk down this trail, I don't suppose you had time to do that, you would see places where the ice had been up to where there was a little temporary bridge that you could walk across it. The bridge now is just slumped over the side of the ridge, down here on the edge, sort of bearing testament to where the ice used to be. So we decided then to study the Zwillingsgletscher, this one here that's kind of right next to the Schwarze Massiv. The reason we wanted to study that one is that it's a narrow glacier. You can see it's fairly narrow. It's truly an alpine glacier in the sense that it's occupying a very narrow valley. And if you can imagine, it's kind of like fluid dynamics. If you're going to look at something that's very narrow, it's going to be moving faster. And that's probably the fastest moving glacier. I don't know that for sure, but just anecdotally based on measurements, sort of like 70, 80, 90 meters per year, something like that. I'm sure people have more precise measurements. But because it's moving fast through the icefall zone, which is just right sort of around the edge of the Massif, you can't quite see it standing here, but there's lots of crevasses. That's where the glacier is actually forming. Because it's moving through that icefall zone fairly rapidly, it's narrow, so it moves quicker, then it can actually pick up seasonal changes in the interior structure because water gets into those crevasses and then freezes, or maybe it doesn't freeze. Maybe it just stays there and retains its latent heat. So now if you kind of look at the surface of the Zwillingsgletscher, you kind of see these ridges, right, going across transverse ridges. If you look at the grid next to it, almost like ripples. Ripples, yeah, but it's not a sedimentological thing, right? Actually, Tom's been out there, so he could attest to this. If you look at the grins, you don't see those so much. That's related to something called ogive. So some of the best times to come out here, but the most difficult, is when it's snow-covered. This was a picture taken that I took from helicopter in May, so it's been about 1 month, maybe 3 weeks ago from this time of year. And then I also applied some image processing, so you see the shading, the shadowing, and that represents the ogives. And what the ogives represent has always been a bit mysterious. People have hypothesized, studied them for years, but there hasn't really been a unifying explanation for what they are. But they're fairly subtle ridges which are enhanced by the snow. So this represents one ogive, or if you think of it as a sine wave, it's one wavelength. So what we did is, working on the snow is of course difficult because you don't know where. It's easy in the sense you can pull a radar antenna, which is what the study is about, but it's difficult because if you step in the wrong place, you just go down, 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 right? And so we would have to rope up and to each other And I don't know, my rope didn't connect to anything. I don't know why that's going. No, it didn't. But I didn't have long poles to see if you're actually stepping in something that doesn't go anywhere. Okay. So, one of the techniques that we found worked quite well is ground penetrating, or in this case ice penetrating radar. I don't want to give you a lecture on radar, but it responds to changes in the electrical conductivity. There's lots more to the story of the substance. And of course, if you have ice versus water, well, there's a huge change in electrical conductivity, or if you're more physics oriented, the dielectric constant between ice and water. Okay. Solid ice isn't very conductive electrically, but water is, as we all know. So for example, if you put an ice cube that's really been in the freezer a long time in the microwave and turn on your microwave, well, it just sits there for a while, right? Doesn't do anything. But if you put just a little bit of water on it, it melts very rapidly. Okay, so that just represents the change in dielectric constant. We use that change in dielectric constant to look at the internal structure of the ice. Now, if the ice were really just ice, like you might ordinarily think of, the solid ice all the way around, all the way down, you wouldn't necessarily see anything.